Next up, we have Hooke's law. Suppose we have a spring and we apply force F on the spring to stretch the spring. The spring is stretched by displacement X. The unstretched position of the spring is, say, our origin, X is equal to 0, referred to as the equilibrium position of the spring. In applying the force F, we introduced a deformation X on the spring. The applied force is equal to Kx, where K is the spring constant or force constant of the spring. Unit is Newton per meter. The force F has the same direction as the deformation X. So F applied is equal to Kx, positive Kx, same direction as F applied. Magnitude of F applied is Kx, K times distance, X. X is the deformation distance of the spring. The spring reacts, third law of motion, the spring reacts by applying a force of the same magnitude but opposite in direction. So F spring, the force applied by the spring, will be equal in magnitude as F applied but opposite in direction. So opposite, so positive Kx, opposite of that is negative Kx. The spring force, the spring will apply a force in the opposite direction. You have spring force F. F is equal to negative Kx. Magnitude, of course, is always positive, so magnitude of the spring force is just K times distance X. This is referred to as Hooke's law. F is equal to Kx. Of course, take note, vector form of this equation, F is equal to negative Kx because F will be heading in the opposite direction as X. If you look at the figure, F, X, they have opposite direction. Just like gravity, spring force or elastic force is a conservative force. When we say conservative force, when we look at the work done gets stored as potential energy. The work done by gravity gets stored as gravitational potential energy. The work done by an elastic force can get stored as elastic potential energy. The work done by a spring is equal to integral of F spring dotted with dx. Since F spring is equal to negative Kx dotted with dx, get the integral, that will give you negative 1/2 Kx squared. The work done by a spring is negative 1/2 Kx squared. And this work done gets stored in the form of elastic potential energy. Elastic potential energy, therefore, is just equal to 1/2 Kx squared. The elastic potential energy is just one more energy that you need to consider when doing energy analysis. So in addition to gravitational potential energy, you also need to consider elastic potential energy. So initial elastic potential energy, final elastic potential energy. And of course, unit of energy is joules. And that's it for now. We'll continue our discussion in the next video wherein we look at examples part of our discussion on elastic properties of materials. So thank you for watching.